Okay. Well, gentlemen, I uploaded 2 videos about mindfulness. Did you go over it? Today I discussed with my undergraduate student and they told me that they learned something about mindfulness. I said, if this is the undergraduate doing so good job, I'm sure the graduate student will be even super. So what did you learn in this mindfulness? What does it mean, mindfulness? How to have mindfulness? Why we need mindfulness? You didn't read, you didn't see it? يعني undergraduate is better than graduate. Undergraduate is too busy, not the graduate, right?
I promise you I will see it and I will discuss it with you next week.
After the break, we can discuss it. On Sunday? Sunday.
Yeah.
We need to discuss it, okay? Please. Anyway. So let's go to the presentation today. Yeah, I think it's already, it's recording, right?
Yeah.
How do you know it's recording?
There's that red.
The bottom, yeah.
Where?
The green. The green.
This one here?
Down.
It says
This
that
one.
dot is blinking, right?
Okay. You are sharing screen, but what is this? The
After sharing screen, there is one red dot that is blinking, right? No,
This
on
share-
the left side, sorry.
this one?
On the left side. Yeah.
This one? There is dot here. It means it is recording.
Yeah.
Good. Space. Okay. Screen is not moving. That's expected. So,
Okay.
okay, now,
Did we do part 5?
no, I think I need to first do that one, and then I'll come to this presentation. So can I stop share here?
You don't need to stop share.
Huh?
You can just go ahead and share the other one.
Okay, go new share.
No, don't do it. You just exit this one and open the other side.
How do you exit it?
Escape.
Just escape, and then
Just minimize this one.
And then where's
PowerPoint.
PowerPoint? This one?
No, this one. Yeah, this one.
No, this one.
No.
No, this one. This one is the one that is
No,
there.
this is not the one. Click this. Click the one on the left. Yeah.
This one?
Yeah.
That's it for five.
MashaAllah. Did we talk about this?
A little bit.
Yeah. We did.
Yeah.
Okay, back to track. Okay. So in here, I think we need to set the structure. Is defined as nodes and number. And therefore, everything is related to the nodes. So you are seeing or you are searching what's going to the node. So if you have a node like this in the structure, basically you have to choose what are the nodes. So you are, this is what I call modeling. You are modeling it. You are modeling the real structure by an element with 2 nodes. And everything is coming here. So you are not worrying too much about here. You are worrying what happened to node 1 and what happened to node 2. That's all. So this load, you have to know how much of this load will go to node 1 and how much of this load will go to node 2. We did this last time and we have an equation for it. Do you remember this? N transpose T, which is the function of the loading, and you have to integrate between 0 to L, right? And now you will tell me how much will go to node 1 and how much will go to node 2, because if you can see this one here is, let me see. Okay, laser pointer. This one is N1 and this one N2. And the whole thing, we call it N transpose, right?
Yeah.
Anytime we say N transpose, it means column. And this one is what? The function. So this one is actually will give you two quantities, like two integral. You can integrate the upper part that will give you for node 1 the load, and then integrate the lower part that will give you for node 2. So this is what's happening. F1x, part of the which will go to node 1 and part of the which will go to node 2. Now, do you know how to do integration?
Yeah.
You just multiply 1 minus x times this function and you integrate. You get this and you get this. And you can have this value and this value. So how much then you can put the limit. L, how much? L, I think 1.5. The length is 1.5, so you substitute and you get N1x is minus 30 and minus 60. So we want to solve for stresses using one element, which is crucial approximation. Not everything, anybody will give you a structure, you go and use one element, right? You are assuming, and instead of beam, you are assuming that you have only two nodes. What is this? No, this is not right. And you will see the answer. So we are modeling the whole cantilever by two nodes connected by line. So let's see. So this is the load. Now what do you need to do? You need to find the stiffness. You have to go to the equation, right? What's the equation? K, right? Is it K? F global equal K global. What? D, U1 and U2. That's it. Now, how many nodes? Two nodes. It means this is 2 by 2. This is 2 by 1. Very simple. It's just like one element. So what is the stiffness? The stiffness, you know what? E A over L, 1 minus 1 minus 1. And we substituted and we found this. Is this correct? The upper part, I'm talking about K1. Is this correct? Yes. Okay. What about the force? If this is the node 1, and this is node 2, and this is a triangle. The triangle, I think this is your X. I think the load is moving in the negative direction. So we already know how much the load at node 1 and how much the load at node 2 after integration. And the load should be in the here. This one is F1x, right? And this one F1y, F1, F2x. Okay, how much F1x? Minus 30, minus 30,000, and the other one is minus 60, right? Okay, minus 30 because x is positive here. So this one here is 30,000, and this one is what? 60,000. But since there is a fixed support, there is reaction, right? So node 2, in node 2, there are two things. There is the reaction, and there is the load that is coming, which is 60,000. So this is what will go. So force in node 1 will be minus 30,000. But in node 2, you will have what? Minus 60,000 plus R, the reaction. So this is unknown reaction, and this is what? The load. So this is the contribution of the load, node 1, contribution of node 2. And of course, U2 is 0. You agree U2 is 0?
Yes.
So how many unknowns here? We have two unknowns, right? Or one unknown? Two unknown. But you want to solve for the primary unknown is what? U1. Forget about reaction. So for U1, you just multiply this row by this column equal to minus 30 and solve for U1. Go substitute U1 and find the reaction. Okay? How do you calculate stresses? Now you found the reaction. Okay. We are interested in stresses. Do you know stresses?
Yeah.
Stress, which is a scalar, equal E times epsilon. E, what is epsilon? We said you have to remember B times what? Times D, or U vector D, displacement. Okay, this is a scalar. This is this is scalar. How do you make the product of this as a scalar? B and D. One has to be row and the other one has to be common. So this is why B, what is B? The derivative of the shape function. From now on, that's until the end of the semester. If I say B, you will say derivative of the shape function. So it's E, the derivative of N1. Do you know what's N1? N1 is what? 1 minus 1? What?
1 over x.
1 over L? X over L. And N2? X over L. So what's the derivative of N with X? Minus 1 over L. And the other one is 1 over L. And now, what about the displacement? U1 and U2. This U2 is 0, so you multiply this row by this column, and already you found U1 from the previous slide. You put it here, and you get 24 megapascal. This 24, the stress in the cantilever, it doesn't make sense, right? If you have a cantilever, and you said that this will go bending like this with the load. First of all, we are assuming that the stress is uniform. The stress at the free end is the same as the stress at the fixed support because you use one member. Does it make sense? This is crucial, right? We know that the cantilever has maximum moment here. So the stress here is higher than the stress here. If you plot bending moment, this is from strength of material, sigma minus my over I, right? So the maximum stress will be at the fixed support and minimum will be at the free end. How come we have only, how much? 24 and it is tension. Now, how do you improve the answer? How do you improve it?
Take more elements.
So what is your next step? Two element?
Divide
Two element? Let's divide to 2 elements. Let's see what would happen if we divide this to 2 elements. Okay, here is 2 elements, okay? How many nodes? 3. So your K will be 3 by 3. Okay, very simple. But now you have to understand that the length for each one is 1.5 divided by 2, right?
Right.
So we first obtain the element force for. Okay, can you tell me what would be the force in node 1, node 2, node 3 now? It would be different now. There are 2 functions. For element number 1, you have to use this. For element number 2, you have to use this. This is one function, and this is one function. And you have to integrate from 0 to L, which is 0.75. And the other one will be from where? From 0.75 to?
1.5.
Are you sure?
Yeah.
Not from 0 to 0.75?
No. Already done it, Sasha.
Okay. If this is what you say, okay, let us see. Okay, now, what is this? Can you tell me? It looks hard to understand, but you see, the load at node 1 is minus 7,500, and the load at node 2 is this plus this. Anybody can tell me what's happening here?
No idea.
No idea. Anybody?
Give us 5 minutes.
You just take the distributed load. This is static, C201. You just take resultant and you just throw it to the node, right? So you come to this element and you put a triangle. You come to this element and you put trapezoid, right?
Yeah.
This one is what, 30,000? Because this one is 60,000. This is 60,000. And this is 30,000. Is this correct?
Yep.
60,000.
The length here is what? 0.75. The length here is 0.75. This is node 1. This is node 2. This is node 2, and this is node 3. So at node 3, at node 2, there would be contribution from element 1 and from element 2. Now you understand. It's like structure analysis. You separate it to two members, right? So how much the load here? We understand. We said we don't want to do integration. We know 1/3 of the load will be here, 2/3 of the load will be here. What about here? You divide it to two. Half of the for this one, half of the load here, half of the load here. For the triangle, 1/3 and 2/3. That's exactly what's happening here. Okay, look at the bottom. Look at the bottom. 3.10.41. You see, did you see 1/3? Did you see 2/3? What is this? This is the total load, 22.5. The area of the triangle. Half of the base times the height. How much? 22,000, right? 500? Half of 0.75 times 30,000. Is it? Huh?
60,000.
What?
60,000.
50,000?
It's not 30,000. 60,000.
60,000? Where is it?
Oh, yeah.
60,000.
And 120. 60 and 120 there.
Where are you? You should tell me if I make a mistake, right? 60,000, right?
Yeah.
Right.
120? No, 60,000 times 0.75 divided by 2. Is it going to be 20?
Yes.
Yeah.
Okay, makes sense. Okay, thank you. Okay, so 1/3, 2/3, we already know it. So what are the load here? Is it to the right or to the left? To the left. To the left. Okay, what about here for node 2? To the left. To the left. Reaction, right?
Yeah.
Reaction. Okay. How much this you said? How much here? Load. How much for node 1? Minus 7,500. Okay. This one.
Minus 15.
150?
No.
15,000.
15,000?
Yeah.
This one.
30,000. Minus 30,000.
You understand? I don't want to go to this trivial things. Come on.
Yeah.
Right? 60,000 times 0.75 divided by 2. And then 1/3 of this. So how much total here?
Minus 30,000.
No, without minus. I know it's to the left.
Yeah.
How much?
30,000.
30,000?
Yeah.
Okay, how much here?
37,500.
30?
7,500.
7,500.
37,000.
37?
Yeah.
37?
500.
00?
No,
5
5
0 0
5? 0?
0.
That's it?
0.
1 0.
0.
Yeah.
Very good. This will give you the forces at the node, which means F1, F2, F3. What about K? You need to find K1, and you need to find K2, and you need to add them, and then you get 3 by 3, right?
Yes.
Yes, you're right. 1, 2, 3. This is the big K. This is the U1, U2, U3 equals.
F1.
Okay, F1, you will put this one here. This one, you add it to this one because there is contribution of node 2 from element 1, and there is contribution from where?
Element 2.
From element 2 to node 2, right? Correct? Never follow, right? Right. I think you feel right. This comes up, right? You have stomach? Okay. You add them up, right? You add them up. Okay, what about node 3? Node 3, it will be this. Okay, so this one will be 7,500, 7,500. How much this? 30 and 45,000?
Yeah.
Okay, the other one will be
7.5.
3. No, it will be R minus. This is minus minus. To the left, to the left. What's minus 3,7,500? Okay, how many unknowns? You'll 2 unknown because U3 is 0. You'll solve for U1 and U2. Okay, let us see. Let us see. What? Go ahead. But go ahead. Okay, great. Thank you. So this one here, wow, this is exactly what we have in the board. You see, F1, F2, contribution from, and this one is the reaction, and this one. Okay, look at K1 and K2, they are the same, and you get K. Finally, we got this. K times U1, U2, U3 equal the forces, right?
Yeah.
Can you find the unknown U1 and U2?
Yeah.
Okay. You take this matrix, is it? Which one?
Yeah.
This matrix?
Partition.
You take this one. 1 minus 1 minus 1, 2 times U1, U2 equal to this and this. No reaction. You solve for U1, you solve for U2, then you can find the reaction. Okay, how do you find the stresses? Now we have two elements. I need to know how much the stress in element number 1 and stress in element number 2. How do you find it? Okay, tell me. All you need is U1, U2, U3. U3 is 0.
Yeah.
Can you tell me how much U1?
0.18
Minus 0.18?
Yeah.
Yeah.
Okay, and the other one?
Minus
Minus
0.75.
0.1575.
Okay. How can you find sigma 1? Sigma at element number 1. We just erased it.
Yeah.
Sigma equal to E times epsilon. Epsilon equal B times the displacement. Okay, for element number 2, sigma for element number 1 will be E times epsilon of element number 1. It will be E, no, B times D. Okay, this one will be E, and this one we already know, 1 over L
Minus 1 over
minus 1 over L. Now what about the D?
U1 and U2.
U1 and U2. Exactly, U1 and U2. That's it? What is L? L is 0.75. That will give you sigma. Can you repeat this for element number 2?
Yeah.
U2 and U3. Okay, let's see the stresses. You must be anxious to see what happened to the stresses. Wow. Stress in element number 1 is 6. And stress in element number 2, 42. How much for when we use element, one element? 24? 24? Average them. 6 plus 42 divided by 2. 24. But it is better, at least, for element number 1, instead of 24, 6 is smaller than 24. And as you go toward the support, which is element number 2, it is getting higher, 42, instead of 24. Oh, what do you want to increase now? Yes. If we increase the element, it would be more. Yeah, it would be even more and more. In fact, the stress here, if you plot the stress, it will be curved. At the tip, it's 0, and it's going like this. This is the fixed support. It's not. Remember, for one element, we got what? 24. For 2 elements, we get 6 and 42. For the other one, you see, at the end, we want to see stairs. Right? Like this. If you divide it to many elements, you are going to approximate this parabola by piecewise. Do we have that? Yes, we have it.
So even in software, when we use like a large mesh,
Yes.
the triangles become like a stair instead of triangle.
Yes. So when you use mesh, it means you are increasing the number of elements.
If you make the segments bigger, you end up with a stair instead of triangle.
Instead of, yeah. Okay. So it's better to use finer mesh to go to the Okay, now you run. I ask you to go to COMSOL, to Abacus, and you run this problem. And you run this problem, and you get very good colors. How do you check if your answer is correct?
Next, your sense.
Huh?
Use your sense.
Use your sense. My sense is okay. My sense says this is okay. And then I'll shake my head. This result is so good. I'm glad. Don't use your sense. You have to.
Logic sense.
No, but he is right.
Logic sense.
If you get high stresses at the tip, this is doesn't make sense. You know how to expect that the stress will be higher and higher as you go. But now you'll ask the quantity, the values, whether they are correct. How do you check your values? You have to go to closed form analytical, and you compare analytical with the numerical. And for cantilever, you know how to do it.
Yeah.
What is the stress? The stress equal the normal force divided by the area. So you just have to find the normal force as a function of x. And you substitute, it will give you sigma as a function of x. And then you can plot it analytically. How do you find n as a function of x? Cut this and flip by the diagram. You see, we cut it, and this is the function, and this is at a distance x. So we want to find the normal form. How do we get it? Summation of f(x) equal to 0, right? So it would be what? 40,000 x squared. So at x equal to 0, the normal force is 0. It means the stress is 0. The normal force would be maximum where at x equal 1.5. Okay, let's compare this with finite element. Okay, this is what? This is only the normal force. How do you calculate stresses? And even if you want displacement, not only stresses, if you want strain, displacement, how do you calculate the displacement? Stress is very easy. N over A, and A is constant. So this is easy. But now how you calculate?
U over
Do you remember this equation? 3.11.1. Do you remember it?
not exactly.
Do you remember that delta equal NL over EA?
Yeah.
This one is valid only. It will give you the displacement, which is the longitudinal displacement. If E is constant, A is constant, and N is constant. Our case, the normal force is not constant. So what you do, we have, that is the formula. U will be 1 over EA, and you have to put N inside the integration. And instead of L, you will have dx. Okay.
We have to
See,
put okay.
that's it. Cancel.
Okay.
If I say okay, it would restart. Say cancel. If I say okay, it would restart after 1 hour. Okay. Now, did you see this? Remember this for this is CE2O3. Have you taken CE2O3?
No.
Mechanics, strength of material.
Not here,
You forget it. Yes, you took it, but you forget it. Long time ago, right? Before you get married, right? Okay.
not here.
Okay. Now this one here is the displacement. So you just take this and you put it here and you integrate from 0 to L. And then you put what? The limit for the integration. When you integrate, you have to have constant.
Yeah.
And the constant from the boundary condition. Already you know the displacement at x equal to 1.5, it is equal to 0.
Yeah.
See? He's integrating and he's putting C1. And it says here, the condition at x equal to L, U equal to 0. He found C1. Take C1, put it back here. Then you will have U as a function of x. See? Look at U. This is U closed form. And this is the stress closed form. This is the analytical result for U and for stress, which is changing with X. Okay, now let's go to finite element. Let's draw for finite element when we have 1 element, 2 element, 3 element, 8 elements, and we see how closer we get to the exact. We will call this as exact solution. The analytical, let's call it as exact solution. Wow, look at here. What is this? Displacement in meters. Okay. When you use one element, it gives you this curve. What does this mean? It's linear. Okay. If you use 2 elements, it will be 1, 2, bilinear. When you use 8 elements, you are approximating the curve with piecewise, right? But look at the exact. Exact is what? It's a curve, parabola, x cubed, right? So which one? Do you think this is good solution? It's not good solution, right? Compared to the analytical one, okay? Yeah, because this is crucial. The first one, you are saying that the country is only 2 nodes. The second one, you are saying the contribution is maybe 9 nodes, okay? Very interesting. So 8 element is good? You think 8 element is good?
No, we have to go more.
We have to go more than 8? Okay. The finite element solution matches the exact solution at the node point. MashaAllah. It's satisfied here. Of course, boundary condition. We put the boundary condition. Okay. And it says here, the reason why the nodal forces, okay, the nodal degree of freedom are exact. Okay, we use that. Okay, number 2. Although the node value for the displacement match the exact solution, the values at what? At location between the node are poor, using finite n for 1 element and 2 element. We see the departure, right? Between the exact. The stress is derived from the slope of the displacement curve. Therefore, by finite element, because u is linear, what's the derivative? If u is linear, what is the derivative of u? Constant. That's why you get stress is constant, because u is linear. You are already assuming u is, that's why for this element, if you use 1 element, the displacement or it's linear. If you choose over each element, it is linear here, linear here, linear here, linear, okay? This is very, very important. It gathers everything. So when you use 1 element, you see 24, stress is 24 for 1 element. How much the length of the element? From 0 to 1.5. Okay, this is 1 element. Where is 2 element? Did you see 2 elements?
Yeah.
And this is 4, and this is 42. Okay, 8 element. 1, 2, 3, 4, maybe 5, 6, 7, 8. Wow, very good. 8 is the dot here. See the dot, the circle?
So 8 not good.
8 is good, right?
Not good.
Not good. So you have to go to maybe 16.
Over.
Sorry?
The problem with running the software.
It will take time. But you want to solve the problem, right? Okay. It will take
more time, but if we go more and more and more, like 16.
What about your project? You're not going to solve cantilever. You will solve a problem that it will stay maybe overnight calculation. Wait until you graduate, finish from this course. Okay. This is just simple thing, right? Okay. And this is, you are using linear elastic. You're not going into non-linear. Now, suppose you are working in a company and they have a problem in a machine and they say, okay, come analyze it. Then you go to COMSOL and you go to Abacus and you make modeling. You said, okay, I learned this from CE 517. And you did your analysis and you show it to your boss. And your boss said, oh, what kind of analysis you use? You told him I use elastic analysis. He said, how come? You see, there is a failure there. Already it goes to plastic range, plasticity. You have to include plasticity. You are outside the elastic range. Now, what about the software? Do they have that?
Yeah.
Yes, they have that. Do you understand plasticity? Where did you take plasticity? 510? Okay, because if you said no, I can offer a course. It's called plasticity because my PhD was in plasticity. I'm mechanical. I'm almost, yeah, half mechanical, half civil. Okay. I used to offer this course about plasticity. Not only plasticity, I can model this as damage. Have you heard about damage mechanics?
Yeah.
Fracture and things like that. Yeah. You can model the material damaging. Every time you put a load, you damage part of it. You create voids in the element. And we create voids you are making it more damage. It's accumulate. And these are things which are advanced. But now you have to understand, if you want to run a problem, you have to see the situation of the problem. If it is elastic, run it elastic. If it's plastic, you have to run it plastic. You cannot use elasticity. You have to use plasticity. And there is this option. Look at this here. The exact is 72. Is the exact 72?
No.
It is 72. We're talking about the fixed support. You
Oh, yeah.
see? Yes. It says here, this is at the fixed end, axial stress at the fixed end. So it is 72, the exact. And you see, when you increase, when you are using one element, it gives us 24. So at the fixed end is 24. When you use two element, the stress at the fixed end is 40. I think many people already took vacation, right? This is why they are not here tonight, right?
They started.
They started it, right?
Yeah.
Okay, so we'll take attendance today. We have 4 elements. When you have 4 elements, we have 60 and 8 elements. Still 8 elements, it's close, but it's not that close. Okay. Okay, what is this here? It's an equilibrium, right? This is for when you choose one element. This is 0 here, and you want to draw free, but this is very, very important. Whenever you calculate stresses, you have to make sure that your element is in equilibrium, because if it's not in equilibrium, you will have a problem, okay? This is kind of check for your answer and for your result. Convert stresses to forces and isolate the element and see if it is in equilibrium, okay? Now let's move to something else. What should I stop share? So that I can continue? I can continue. So I just come here and click on this one.
Yes. It's sharing the entire screen.
Yeah. It's
Not the window.
Is this the one?
Yeah.
This one?
Yeah.
Okay. This one is very interesting. What are the 3 methods to calculate the stiffness? One of them is direct method. The other method is what? Potential, pi. Pi with x with u and pi with u2. And then you find 2 by 2. What's the third method? Galerkin. This is what we want to do tonight. And that's it, okay? We want to derive the stiffness for the bar element using Galerkin method. And I think you know the answer. What's the answer? What's the stiffness for the rod? What? A? K will be EA over L. 1 minus 1 minus 1 like that. Okay. Now, although the Galerkin method, we are going to do it for the rod, but we are going to use it to derive it for the beam. If you understand it now, you will have easy time. Okay, very, very important. And normally it comes in the exam, Galerkin method. Okay, very good. Let's see. It's ahead of time. Open, close, part of it close, part of it open. Combination. Interesting. It will be interesting one. Okay, let's see here. You understand? So the Galerkin method is based on what? Of course, the Galerkin is the guy who discovered this method. The name of the person who discovered that method is called Galerkin. Just like Mohr circle. Mohr is the one too. Okay? Very good. Okay. The Galerkin method, it's called residual method. You want to minimize the error. It's minimization of error. Mathematically, talking about Galerkin method is minimization of error. Do you have error? Yes, we have error. You have seen the error when we use 2 element, 3 element, and we are approximating the analytical U by approximate U. So, if you have differential equation like this, I will just put any differential equation, because at the end, finite element is solving differential equation. This is what finite element. Finite element is a tool that can solve what? physical problem after you transform it into what? Differential equations, okay? So let me give you this differential equation. P second u dx squared minus, let's say, 4 dy dx plus y equal to 100. This differential equation. And to solve this analytically, you need two boundary condition, right? Then you can get this analytically. But the problem that sometimes you cannot solve this differential equation on the whole domain because the domain is complicated. Complicated in geometry, complicated in terms of loading. So you have to use finite element. Now, if you do closed form, you have to tell me this is not right. This is you. Come on, guys. I put you here and y here. And you said yes, yes, yes.
You there.
You.
You. Do not want to interrupt you.
What do you mean you interrupt? Interrupt me. If there is something wrong, interrupt me, okay?
Next time we'll do.
So where are you?
You.
Watch it. This is you. This is you. You're independent. Your unknown is you, right? You want to get u as a function of x. Okay? So this u, if you use closed form solution, then this will give you minus 100. It will give you 0. Do you agree?
Yeah.
If the differential equation is this minus 100 equal to 0, if you take this u and you substitute here, it will give you 0. What about finite element? If you take u from finite element and you put it back in the differential equation, do you think it will be equal to 0? Approximately.
Yeah. 0.0.
Error. It will give you error.
Yeah.
That error, we call it residual R. So if you put u bar, and u bar, you get it from where? Finite element. This is not equal to 0. What do you call this? You call it residual R. And exactly, residual R, not equal to, it's close to 0, but it's not 0. So you want to minimize it now. We want to minimize the residual error. So how do we minimize the residual error? There are 3 methods to minimize the residual error. One of them is Galerkin method, and there are 2 more other methods. So we'll explain only 3 methods. That's all. Okay? Very simple. And everything has to do with what? With R. Everything has to do with R. So let me read this thing for you, because if I read it, you will understand what I said. By the way, I am putting something in my ear. If you hear me, my voice is so loud because I don't hear myself. Okay? That's why. I'm not annoying you with my voice, right? Okay, good. Very good. So it says here, general formulation. We developed the bar finite element by the direct method. Yes, we developed that. And by the potential energy method, yes, in this section. In field other than structures or mechanics, it is quite probable that a variation principle analogous to the principle of minimum potential energy, for instance, may not be known or exist. Potential energy in some other field, they don't have potential energy. Like in the electrical, like in fluid, like in this, they don't have potential energy. So they have to use what? They have to use other method. What is the other method? Exactly. You see, in some flow problem, what is the water? Water people. In flow, right? In flow, porous media, the movement of the oil in the rocks, okay? All of this flow problem. So in flow problem, fluid mechanics, and in mass transport like heat transfer. Okay, do we have mass transport in civil engineering? What is it? What? Traffic, okay. What else? Evaporation of the concrete, right? Chloride going inside, corrosion. This is called mass transport. So in mass transport, I'll give you, okay, give me potential energy for mass transport. There's no potential energy. There is only differential equation. So how to get the stiffness? You have to use Galerkin method. See how powerful it is? You cannot escape from it, right? You cannot escape. We often have only the differential equation and boundary condition. However, the finite elements still applied. Okay, the method of weighted residual applied directly to differential equations to be used to develop finite element. In this section, we describe Galerkin residual method in general and then apply it to the bar. So we'll explain it in general and then we have an example. Okay, if we can get EA over L 1, 1, minus 1, minus 1 tonight, we'll be happy. Okay, the development provide the basic for later application of Galerkin method to what? To beams element in chapter 4 and to the non-structural heat transfer element mass transport in chapter 13. Because of the mass transport phenomena, the variation is not known or Galerkin method is necessary to apply for the development. You understand now why it is Galerkin method is important?
Yeah.
Okay, because in some cases we don't have. This is it. Everything in this slide. You see the residual R, the one I put in the board?
Yeah.
You have to integrate the residual over the volume and you make it equal to 0. It's true that R is not 0 because you put the approximate function. But now take residual here and integrate over the volume and equate it to 0. That will give you the stiffness. So you are looking for the stiffness, which will make what? Which will make the error over the whole volume to be equal to 0. It may not be equal to 0 over small element, but the whole structure, it will be equal to 0. So what is this R here? Okay, so let's read this, please. The weighted residual method, a trial or approximate function is chosen to approximate the independent variable, like U bar. It's not exact, such as displacement or temperature in a problem defined by differential equation. The trial function will not in general satisfy the governing differential equation. Of course, there is an error. Thus, substitution the trial function, which is U bar, in the differential equation result in residual R over the whole region. Take this R and you have to make it minimum. One of the conditions to make it minimum is to put it equal to what? 0, right? You see, when you put it equal to 0, then that's it. That's Galerkin method. Okay, if the residual method, we require the weighted value of the residual. What's the difference between this one and this one? Did you see anything? Ah, the W, right? Did you see it? Here, not there. Here in the. This one has no. This one, you want to minimize the residual over the volume. But to make it 0, you cannot just simply cross minimum and put 0. It's not up to you, mashallah alayk. You just put 0. You have to do some work. You have to multiply it by W and then put 0. It's okay. What is this W? This W is weighted function. Weighted function like alpha, beta, gamma, weighting. Just like interpolation function. You remember the interpolation function?
Yeah.
That's it. This is like interpolation function. This W not necessary to be scalar. It can be function of space, function of X. Okay? So, still we don't see Galerkin. We only see the concept, right? Using Galerkin method. Galerkin method says, okay, I am going to put instead of W, which is the weighted, I'm going to put the shape function. MashaAllah alayh. He's so clever. He said, why I don't use N1, N2? That's it. So this equation becoming like what? 2 equations, because you can integrate R N1 dx from 0 to L, this is equal to 0, and then R N2 dx equal to 0 from 0 to L, that will give you another equation. And then you can generate the stiffness, okay? Because this one here
is WI. WI, which means for each node.
Okay, so you are going to make minimization of the error at each node to be equal to 0. And he said, okay, using Galerkin method, we choose the interpolation function, such as this in terms of, instead of W, Ni, which is the shape function. And already you know the shape function, 1 minus x over L and x over L. Okay, and look here, he says R and I equal 1, 2. It means 2 equations, right? ها؟ لا لا اللي مكتوب على السبورة 1 2 3 depending on how many nodes, okay? So it means if you have a structure with 100 nodes, it means and it will be 100. It will be 100. But for one element, it will be 2, right? For the rod. Because you are talking about the stiffness of the node, of the rod with 2 nodes, right? So this one here, you are going to minimize this not over the whole structure, over the element. You are minimizing that over this element, minimizing over this element, minimizing over this element, independent. And therefore, yeah, this is why you have stiffness here, stiffness here, stiffness here. Okay. It says equation, this result in total of n equation. In our case, result in 2 equations. Apply to the node. Okay. To obtain boundary, we apply integration by parts. Do you know integration by parts?
Yes.
By the way, Galerkin method always use integration by parts. Because why you have to integrate by parts? You have to have differential equation. And when you integrate differential equation, you reduce the number of the order, right? If it is dy dx and you integrate, it's becoming y, right? So this is why you have to do it integration by part. So you reduce the order. Now, do you remember this equation? Anybody? MashaAllah. Do you remember this equation? 3.12.4. What is this equation? What does it tell you? This is a differential equation, and it is equal to 0. When you put u exact, it would satisfy this. What is this? Read the title. Bar element formula. This is for the bar. It means that the tension in the bar is constant, and when you take the derivative, it will be 0. What is A? What is du dx? Strain. Take strain multiplied by E. Epsilon, right? Strain times E is what? Sigma. 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 Sigma times A. Force. In the rod, the force is constant. So when you take the derivative of the tension force, it should be equal to 0. MashaAllah, see how they find a differential equation for the rod? This is the tension. It means T, if you have a rod here, if you have rod with this node and this node, thrust element, tension here equal constant. So such that dt dx equal to 0. The derivative of a constant value is 0. This one here is t. You take the derivative, it will be 0. Okay, so assume that you don't have the exact u. If you don't have the exact u, then if you put any u other than the analytical, it will not give you 0. It will be r. R times the weighted function dx, because you are using length, not volume. If you integrate over the length, it should be equal to 0 at node 1 and at node 2. How many equations here? 2 equations? Okay. How do we do this? You will tell me it's complicated. Okay. Do you know you? You have to integrate with respect to x. What is x? Can you tell me what is x? A is constant. E is constant. Okay. Okay. What is the derivative here? It's second order. Do you agree? Because this is d dx and this is du dx. It's second order. But when you integrate second order by part, it becomes first order. That's the beauty about it. Okay, anybody will tell me u as a function of x? Can you tell me u as a function of x so that I can integrate? Can you tell me n as a function of x? Because I have to integrate with respect to x. So this has to be function of x and this has to be function of x. Do you know it? Aywa, will you? Do we know u as a function of x? What is it? Look at the right answer. Exactly. U equal n1 times u1 plus n2 times u2. That's exactly what you said. So you know the shape function. Once you know the shape function, you know. So ux is n1 u1 plus n2 u2. n1 is function of x times u1 plus n2, which is function of x u2. And n, you know it already, n1 and n2. So everything is function of x. Now you can integrate. But the whole idea is not to go explicitly. Don't go like this. And you say, okay, the second derivative of u. Okay, make the second derivative of u. What will give you? It will give you 0. If you think you are smart, you're going to substitute, mashallah. You will take it out, and you say, okay, very easy. This is the second derivative of u dx squared. It will get 0. You'll get nothing. That's why you have to rely on integration by parts. Okay, do you remember this? I think it's u dv equal vu, if I remember, minus integration of v du, right? You have to use this. And even in the beam, we'll use integration by part. For heat transfer, we will use integration by part. For vibration, we will use integration by part. Okay? For eigenvalues, for stability, everything we'll use integration by parts. Okay, let's do integration by parts. That's it. Do it. Okay? Integration by parts. So that's it. U dv, we separate it. U will be in I. And dv is this. This is what you have inside the integral. You have this quantity and this. Is that right? That's what you have. Okay, let me convince you again. See? Which one is u? In I. And dv will be d dx, ea du dx, dx. Okay? So if you integrate by parts, look, if you integrate by parts, what happens if you integrate by parts? You have to equate it to 0. It means what? U dv equal to 0. It means uv minus integration of v du equals 0. Integration of u dv should be equal to 0. So it means what? It means the right hand side uv minus integration of v du equals what? 0. Yes, it's equal to 0. So this one here is what? uv minus integration of v du. Okay. How many equations is this? How many equations is this? Watch the I. The I, we said sub I. I means how many equations? 2 equations. Right? Did you see it here? Not here. It's here. So this is I. This is I. Okay. So this one will give you 2 equations. Okay. Can you tell me the first term how it would be for node 1? Just tell me what would be this for node 1. Yeah. And then I will finish the rest. So what do you do? For node when I equal to 1. When I equal to 1, you replace I by 1. Okay. Replace I by 1. So it will be what? N1. N1. EA. Okay, EA. And then what? Du dx. But u we said du. What is u? U is n1 u1 plus n2 u2, right? And then what? And then we put the limit from 0 to r. Okay, n1 ea. Okay, can you take the derivative here? It would be derivative. U1 is not function of x. U1 is an unknown value. It will be what? dn1 dx. You already know the derivative of the shape function. So it would be what? Minus minus 1 over L.
Yeah.
U1. This one plus 1 over L. U2. Right? And this from 0 to L. Yalla, evaluate. Yalla, can you evaluate? Put L. Can you put L?
Yeah.
What?
The first.
How much the value of N1 at L? Huh? How much the value of N1 at L?
1 minus 1, 0. 0.
How much the value of N1 at L? 0, because N1 is varying like this. This is node 1, this is node 2. It has a value of 1 at node 1 and has the value of 0 at node 2, which is L. So the value of N1 at L equal to 0. So you are multiplying 0 of all of this, it will be 0. Minus. Now put the other limit, 0. What is the value of N1? 1. EA. Then, can I put it minus 1 over L and 1 over L? And I put U1 and U2. Can I put it like this? Okay. Have you noticed something? There is something, right? There is EA and there is L, which we will put it outside. And there is 1 here and minus 1. Okay, let's see what happened to these equations, okay? So, you see, that's exactly what we have. So when we do this and we put the limit, we get this equation here, okay? So, N1 equal to 0 at X, N1 equal to 1 at X equal to 0. So we get this equation. What is this equation? This is for N1. Can you repeat things for N2? You just put here instead of N1, N2. And instead of N1 here, you put N2. You get another equation like this. Where is it? It's here. Okay, let's put the first equation. So from when you put N1, can you tell me what is what is this one here? This one. That is not N1.
AE over L.
EA over L. U1 minus U2 equal F1X.
Yeah.
Okay, what about if we put instead of N1, N2? Okay, EA over L, U2 minus U1, F2X. Okay, can you put it in a matrix form? F1X, F2X equals something times U1, U2. What? 1, 1 minus 1 minus 1.
Yes.
Is that right? Do you agree? He's right. Okay, good. So we got it. Let's see. Very good. So how many minutes we have? This is the other ones. Okay, the other ones. Here we integrate what? We take the residual. We said minimization over the volume. That is what called Galerkin. There is another method. It's called, you see, this one here, that you are going collocation method, that you are going to satisfy it at a certain point. We'll talk about it next class. I don't want to rush it, but it is easy. And the third method, just before, it's called subdomain. So there is no integration in collocation method. You just want to make it 0 at a certain point, at node 1 and at node 2. That will give you 2 equations with 2 unknown. Okay? Collocation, this collocation method. Subdomain method, instead of integrating over the volume, you integrate over subdomains. Okay, different. Okay, and then you find it. Okay, so we'll talk about this, but the most important and then least. Have you heard about least square? Least square method. Numerical method. We will use it here. Anyway, forget about this other method. I have to review it after you come back from the break. Okay, and Galerkin method is so powerful, right?
Right.
It will be powerful when you go home and read it again. Yeah, I know. You only get 30% of what I I said, right? Okay. Now let me Stop share first, and then stop recording,